Welcome to our lesson on line integrals in R2. Line integrals are an extension of what we learned in Calculus 1, where we integrated a function along the x-axis. For our line integral, we'll integrate a surface f of xy along a curve in the xy plane. So if f of x is continuous in a region containing a smooth curve C, defined by r of t as we see here, and t is on the closed interval from a to b, then we can integrate f of xy along the curve C with respect to arc length by evaluating the following integral. And there are several things to notice here. First, notice the function f of xy is rewritten as a function of t by replacing x with x of t and y with y of t, where x of t and y of t come from the components of the vector valued function r of t. And then differential s is replaced with the magnitude of r prime of t dt. And this should look somewhat familiar because we did do this when we were determining arc length earlier in the semester. And of course we can rewrite the magnitude of r prime of t as the square root of x prime of t squared plus y prime of t squared. So you can think of the result of a line integral as the area of a fence that is built along the path of a curve in the xy plane with a variable height given by the function f of xy. So it's not like this fence we have here that's straight and has a fixed height. It would be a fence that takes a path of a curve, and the height of that fence would vary based upon the function f of xy. For example, in this graph here we see a blue surface, and if we integrate this surface along this red line here, it would give us the area of this yellow plane that is below the blue surface. And this will be the result of our first example. Let's go ahead and take a look at it. We want to evaluate this integral along C, where C is from the point 0, 0 to the point 2, 4. So I've already sketched that segment here. Here's 0, 0. Here's the point 2, 4. Notice that the slope of this line would be up 4, right 2, or 2. So the equation here would be y equals 2x. So the first thing we need to do is parameterize this path in the xy plane. Well, if we let x equal t, and if x is t, y would be 2t, and t would be on the closed interval from 0 to 2. So if we want, we can rewrite this as r of t is going to be equal to t comma 2t, and t is on the closed interval from 0 to 2. Now we need to rewrite f of xy in terms of t, and then replace differential s with the magnitude of r prime of t dt. So our limits of integration will be from 0 to 2. X is equal to t plus the square root of y is going to be the square root of 2t. And then differential s is equal to the magnitude of x prime of t squared plus y prime of t squared. Well, x prime of t would be equal to 1, and y prime of t would be equal to 2. So we'll have 1 squared plus 2 squared dt. Let's go ahead and simplify this. Here we have the square root of 5. This will be t plus, I'm going to write this as 2t to the 1/2. Now let's go ahead and evaluate this on the next page. So the antiderivative of t would be t squared over 2. Here we'd have a u substitution. So here we'll have an extra factor of 1/2 when converting to u. So we'll have 1/2 times, this would be u to the 3/2 divided by 3/2, or times 2/3 u to the 3/2, but u is really 2t. Evaluate this at 2 and 0. This simplifies nicely here. So when t is 2, we'll have 2 plus, this will be 1/3 times, this will be 4 to the 3/2 power, minus, and then when t is 0, these are both 0. So 4 to the 3/2 This will be 4 to the 1/2. That's 2 raised to the third power. It's 8. So 2 plus 8/3. 2 is the same as 6/3, so this will be 14/3. So 14 square root of 5 all over 3. And again, what this represents is the area of this yellow plane below the blue surface integrating along this red line in the xy plane. Let's take a look at another example. On this example, we want to integrate the following function along the curve x squared plus y squared equals 4 in the first quadrant counterclockwise. So we want to integrate 2xy cubed along the curve here in the first quadrant. Well, we know points on the unit circle are cosine theta comma sine theta. So for this circle, if we let x equal 2 cosine theta, or 2 cosine t in this case, and y equal 2 sine t, that would give us this circle as long as t is on the interval from 0 to pi over 2. So this tells us r of t is equal to 2 cosine t, 2 sine t. And we'll also need the derivatives of x of t and y of t. So x prime of t would be negative 2 sine t, and y prime of t would be 2 cosine t. Let's go ahead and set up our integral in terms of t now. Limits of integration will be from 0 to pi over 2. We need to rewrite 2xy cubed in terms of t using our equations here. So we're going to have 2 times x, which is 2 cosine t. And then we'll have y cubed, so we'll have 8 sine cubed t. And now we're going to replace differential s with the magnitude of r prime of t. So we'll have the square root of x prime of t squared. That's going to be 4 sine squared t plus we'll have 4 cosine squared t. Let's go ahead and evaluate this on the next page. Here, if we factor out the 4, we're left with sine squared t plus cosine squared t. This will be 1, so we'll have the square root of 4, which is 2. So all of this gives us a factor of 2. We have a factor of 2 here, a factor of 2 here, and a factor of 8. That's 64. So we'll go ahead and factor out a 64. That'll leave us with cosine t sine cubed t. Now if we will let u equal sine t, differential u is equal to cosine t, which is good. Du is equal to cosine t dt. So all of this is du, and this would be u to the third. So I'll have 64 times 1/4 u to the fourth, but u is sine t. Evaluate this at pi over 2 and 0. 64 times 1/4 is 16. And the sine of pi over 2 is equal to 1, so we'll have 1 to the fourth minus sine of 0 is 0. So this is equal to 16. And so what this represents is the area of this yellow region here that is below the blue surface along the red curve here in the xy plane. That's exactly 16 square units. And that's going to do it for this first video on line integrals in R2. We'll next take a look at line integrals in R3. I hope you found this helpful.